This article is about the transpose of a matrix. For other uses, see transposition note. That this article assumes that matrices are taken over a commutative ring. These results may not hold in the non-commutative case. In linear algebra, the transpose of a matrix A is another matrix created by any one of the following equivalent actions. Reflect A over its main diagonal to obtain it. Write the rows of A as the columns of it. Write the columns of A as the rows of it. Formally, the ith row, jth column element of it is the jth row, ith column element of A. If A is an m times n matrix, then it is an n times m matrix. The transpose of a matrix was introduced in 1858 by the British mathematician Arthur Cayley. Examples. Properties. For matrices A, B and scalar C, we have the following properties of transpose. The operation of taking the transpose is an involution. The transpose respects addition. Note that the order of the factors reverses. From this one can deduce that a square matrix A is invertible if and only if it is invertible, and in this case we have T equals -1. By induction, this result extends to the general case of multiple matrices, where we find that T equals actic -1T, A2T, A1T. The transpose of a scalar is the same scalar. Together with this states that the transpose is a linear map from the space of M times n matrices to the space of all n times m matrices. The determinant of a square matrix is the same as that of its transpose. The dot products of two column vectors A and B can be computed as the single entry of the matrix product, which is written as I by an Einstein summation convention. If A has only real entries, then ATA is a positive semi-definite matrix. The transpose of an invertible matrix is also invertible, and its inverse is the transpose of the inverse of the original matrix. The notation A-T is sometimes used to represent either of these equivalent expressions. If A is a square matrix, then its eigenvalues are equal to the eigenvalues of its transpose since they share the same characteristic polynomial. Is a symmetric matrix. Special transpose matrices. A square matrix whose transpose is equal to itself is called a symmetric matrix. That is, A is symmetric if a square matrix whose transpose is equal to its negative is called a skew-symmetric matrix. That is, A is skew-symmetric if a square complex matrix whose transpose is equal to the matrix with every entry replaced by its complex conjugate is called a Hermitian matrix. That is, A is Hermitian if a square complex matrix whose transpose is equal to the negation of its complex conjugate is called a skew-Hermitian matrix. That is, A is skew-Hermitian if a square matrix whose transpose is equal to its inverse is called an orthogonal matrix. That is, A is orthogonal if transpose of a linear map. The transpose may be defined more generally. If F, V, W is a linear map between right R modules V and W with respective dual modules V and W, the transpose of F is the linear map equivalently. The transpose TF is defined by the relation where is the duality pairing. This definition also applies unchanged to left modules and to vector spaces. The definition of the transpose may be seen to be independent of any bilinear form on the vector spaces, unlike the adjoint. If the matrix A describes a linear map with respect to bases of V and W, then the matrix it describes the transpose of that linear map with respect to the dual bases. Transpose of a bilinear form. Every linear map to the dual space F, V defines a bilinear form B, V times Vf with the relation B equals F. By defining the transpose of this bilinear form as the bilinear form TB defined by the transpose TF, VVIE, TB equals TF, we find that B equals TB. Adjoint if the vector spaces V and W have respective non-degenerate bilinear forms BV and BW. A concept closely related to the transpose, the adjoint, may be defined. If F, VW is a linear map between vector spaces V and W, we define G as the adjoint of F if G WV satisfies these bilinear forms, define an isomorphism between V and V, and between W and W, resulting in an isomorphism between the transpose and adjoint of F. The matrix of the adjoint of a map is the transposed matrix only if the bases are orthonormal with respect to their bilinear forms. In this context, many authors use the term transpose to refer to the adjoint as defined here. The adjoint allows us to consider whether G WV is equal to F-1 WV. In particular, this allows the orthogonal group over a vector space V with the quadratic form to be defined without reference to matrices as the set of all linear maps VV for which the adjoint equals the inverse over a complex vector space. One often works with sesquilinear forms instead of bilinear forms. The Hermitian adjoint of a map between such spaces is defined similarly, and the matrix of the Hermitian adjoint is given by the conjugate transpose matrix if the bases are orthonormal. Implementation of matrix transposition on computers. On a computer, one can often avoid explicitly transposing a matrix in memory by simply accessing the same data in a different order. For example, software libraries for linear algebra, such as BLAS, typically provide options to specify that certain matrices are to be interpreted in transposed order to avoid the necessity of data movement. However, there remain a number of circumstances in which it is necessary or desirable to physically reorder a matrix in memory to its transposed ordering. For example, with a matrix stored in row major order, the rows of the matrix are contiguous in memory and the columns are discontiguous. If repeated operations need to be performed on the columns, for example in a fast Fourier transform algorithm, transposing the matrix in memory may improve performance by increasing memory locality. Ideally, one might hope to transpose a matrix with minimal additional storage. This leads to the problem of transposing an n times m matrix in place, with O additional storage or at most storage much less than Minnesota. For nm, this involves a complicated permutation of the data elements that is non-trivial to implement in place. Therefore, efficient in-place matrix transposition has been the subject of numerous research publications in computer science, starting in the late 1950s, and several algorithms have been developed.